Next topic is the derivation of flexure formula. So bending. So we'll derive an equation for bending. So before starting, we shall have some assumptions of simple bending. The beam is assumptions in simple bending. First one, the beam is initially straight, no curvature in the beam. That means that beam has to be straight for for derivation. Second one, the beam of material of the beam is homogeneous. That is, same physical properties throughout. Means it should have same physical properties throughout the material. It should not change at any point. Third one, the material of the beam is isotropic. That is, same elastic constants throughout. It means that it should have same Young's modulus, same Morse rigidity throughout the beam. There should not be any change. Fourth one, elastic limit of the material is not exceed. So that means any section of material, it does not exceed the elastic limit. It should be well within the elastic limit. It should not go towards the yielding limit after yield, or it should not cross the elastic limit, and it should not go into the plastic stage. Fifth point, the beam bends into a circular arc after loading. So when you apply the load, the beam should take a shape of a circular arc when it is loaded. Sixth one, the radius of curvature is large compared to the span of beam. The radius of the curvature should be large compared to the span of the beam. It means that the arc should be very small. The arc should be very big. Seventh one, the beam is subject to pure bending. So these are some of the assumptions in simple bending. So next is I. I is a moment of inertia, or it is nothing but ability to resist bending. So larger value the I, less the bending. I is nothing but summation of arbitrary area over the radius, square of the radius from the axis of rotation. Summation of integration of y square by dA. Let M be the moment of resistance. That is bending moment, simply bending moment. I is moment of inertia of beam, cross section about Na. Sigma B is the bending stress. E is Young's modulus. R is the radius of curvature of the neutral layer. So consider the beam PQ, arbitrary area, arbitrary length AB. NO is the neutral axis, original before bending. MN is a arbitrary strip above the axis. That is before bending. The figure shows after bending A B dash of a cantilever beam. EMO NO is the Neutral axis Mn is the axis is the layer above neutral axis at a distance y, and so the beam is bent by angle theta, and the bending radius is r, radius of curvature r. So the fiber or layer is from neutral axis. So strain in the beam is change length by horizontal length. Strain, that is epsilon b equals to mn minus mo no upon mo no mn. Something but r plus y into theta, that is r is equals to radius into theta. So the radius is r plus y into theta. MONO is r theta, radius into theta upon r theta. So multiplying the theta inside, r theta plus y theta minus rho theta upon r theta, we have r plus rho minus rho get cancels, we have y theta by r theta, or we just have y by r. So strain beam is y by r. Also, strain beam is stressing the beam upon Young's modulus. Therefore, we have stressing sigma b upon E equals to y by r, or sigma b equals to E by r, sigma b upon y equals to E by r, or sigma b equals to E r upon into y. Consider a beam with the arbitrary cross section. So consider the same beam with the arbitrary cross section, that is the D cross section, and with the arbitrary area dA at a distance y from the neutral axis. G is the axis. So the force acting on this element area delta F is sigma stress into we know the stress equals to force by area, or force is stress into area. It is the delta F is stress, bending stress sigma b into delta area. So bending moment at this about this force delta m is sigma b into delta a into the y distance y. The moment of resistance m is summation of sigma b y dA. And from the equation sigma b, we know that ER into sigma b is nothing but ER upon y into y. Also, showing the sigma b in the equation, we have summation integration of ER into y dA, or equals E, so integration of ER into y squared dA. Integration of integration of y squared dA is I. So therefore, we have m equals to ER into I, or in simply I equals to ER is the second equation. Equating 1 and 2, we have m by I sigma b by y equals to ER. This is the famous bending equation, or flexure formula sigma b equals to m by into y. So bending stress is directly proportional to its distance from the neutral axis. Bending stress is maximum if y is maximum, and it is maximum at the extremities. If sigma d is permissible at design stress, sigma d should be less than the sigma max. But m by I y max equals to should be less than the sigma max. So m by y max equals to sigma d. M by I m into m by y max sigma d equals z into sigma d, where z is the section modulus representing strength per mm cube. I by y max. And flexure rigidity m by I equals to E by r, m equals to EI upon r. Flexure rigidity. Resisting moment EI. Larger the EI, larger resisting moment.